In last lecture, we have started with design of compression member, and we have seen the numerical examples based on design of single angle section or the strut member, design of strut member using single angle section as well as using double angle section. Today we will see how to design the columns. Now for design of columns, we never select angle section. We either select eye section or channel section depending upon how the load is acting on the column. How means whether it is purely the axial load or whether it is a eccentric load. If there will be eccentric load, the column will be subjected to movement also along with the axial load. So in that case, we normally don't use a single section, single eye section or single channel section. We normally go to the built up section. Okay, so what is the concept of built up section, how these are designed, that I will explain you today. The problems based on the same, that is the design of built up section, is not included in your syllabus. We will consider only the design of column as a part of the syllabus. So let me present the screen. We'll directly solve one example for design of columns. As I explained last lecture, the design steps for design of column is exactly similar to that of the design steps for double angle section. So if you remember the design steps for double angle section, um, based on the area requirement, we select the section first, then we check the section classification for the selected section, then we decide the buckling class for the section. Depending upon the support condition, we decide the effective length for this section or for the given column, and based on the buckling class and effective length, we calculate the slenderness ratio, and by making use of suitable tables either or by using the formula, we find out the FCD value, which is the design compressive stress of the member, and then finally we calculate PD, that is the load carrying capacity of the section. Okay, this is the design process. Now many times, instead of designing the section, the problems may be asked like, find out what is the capacity of a section. In that case, the section will be given in the problem statement, and the load acting in the section is also given. So if the section is already given, it means you are only supposed to calculate FCD directly. So all these steps are not actually expected, that select the section. There is no question of selection of section because the section has been given in the problem already. Okay. So for given section, what is the effective length, what is the buckling class, then based on these values, what is the slenderness ratio, then FCD value. You have to suppose you are supposed to calculate FCD only, and based on FCD and area, calculate PD and compare that value with the force acting in the member. And depending upon that, whether you have to write down whether the given section is sufficient to resist the force, or the section is not safe or not sufficient, and the section is required to be revised. Okay, so I have purposely not considered the problems based on the capacity, because the process is similar. Okay, only the initial steps will change. So we will solve now the design problem directly. Can you see the word file whatever I have presented here?
Yes, ma'am.
Okay. So this is the problem statement. I'm just reading it. A column in a building is subjected to factored axial load of 800 kilonewton. It is of 5-meter height, hinged at both ends and braced at mid height. We correct this, mid height, for restraint against buckling about weaker axis. Design the section. Okay. So the load acting in the column is also given, the height of column is given, the support conditions to the column are also given. We are supposed to design the section. So let us start with the calculations. The first step, what is the first step? Can you tell me what is the first step?
Assuming FCD.
Yes, we have to assume the FCD value. So for column, what should be the value? FCD
160 Newton per mm square.
Hello,
Yes, ma'am.
am I audible?
Yes, ma'am.
Huh. Okay, I lost my connection meanwhile, so okay. So what should be the value of FCD?
160.
Yes. So let us assume the FCD value and let us calculate the area required. So I will write down here, assuming FCD equal to 160 Newton per mm square. So AE required will be equal to P upon FCD. So the P force, the force in the member is already given as 800 kilonewton. So it will be 800 divided by 160, or 800 into 10 raised to 3, because this is in kilonewton, divided by FCD 160. So what is the
5000
AE
mm
required
square.
value? 5000 mm square.
Mm square. Then for column we use means double C sections or single.
For columns which are subjected normally more than the load of say 1500 kilonewton, we normally go for double I section or double channel section. But if the load is lesser than that, we can go for the single I section or single channel section. Compared to the I and channel, normally it is always preferred to use I section because of the symmetry in the cross section. I section is symmetric about both the axes, whereas channel section is symmetric about only one axis. So for columns, normally we prefer I section, because for the same given cross sectional area, if instead of I section you are using channel section, the load carrying capacity of the section is lesser as compared to I section. This is because of the change in shape of the cross section, because there is it is a non-symmetric section about one axis, so your moment of inertia also changes. For channel section and I section, if you are considering two sections having same cross sectional area, the moment of inertia of the I sections are normally better than channel section, and hence the load carrying capacity of I sections are more as compared to channel section.
And then for what load you said 150 kilonewton.
1500, 1500.
Okay, ma'am.
Okay, so we will select the section. Now just open the steel table. I forgot to open the steel table here, so give me 1 minute. I will open the steel table. So in the steel table, you just open the pages where the properties of I sections are given here, and you find out a section whose area is greater than the required one. Now required area is 5000 mm square, that is 50 centimeter square. So find out the section having area greater than 50 centimeter square.
And ISLB 325.
ISLB
325.
325. The area is 54.9. Okay. That also we can select, but uh, normally, see, this is a ISLB light weight beam, medium weight beam, heavy weight beam. Normally we select for the column sections. Okay. So let us consider the ISHB. See, there is no any fixed criteria that we should not select ISLB or ISMB. I am selecting here ISHB because I have already solved this problem and I'm having all the answers. So it will better for me to give you the complete safe design problem. You can try, Onkar, you can select that section and you can try with the further calculation. Okay.
Yes, ma'am. Ma'am, but
So
in general, column is having heavy section only.
no, not necessarily. Not necessarily. I choose ISHB normally, but ISLB, ISMB also can be selected for columns.
Okay.
Okay, so ISHB 225, see the area. Sorry, ISHB 225. See, there are two sections. ISHB 225 43.1 and ISHB 225 46.8. These two values are nothing but the weight of the section. So the section having same depth but different weight are there. The difference in the weight is because of the area change in the area. Okay, so I will go to the higher section, which is 59.66. Um, See, one more criteria or one more thing we need to keep in mind, that when we design any sections or especially columns which are subjected to purely axial load, we need to also consider what is the length of the section. If the length of the section is higher, it is always better to select the section having more and more cross sectional area. See, both these sections, now if you observe in this steel table, ISHB 225 about 43.1, this is having the area 54.94 centimeter square. That also we can select. And the second one is having the area 59.66 centimeter square. That also can be selected. I will go to the higher value because see, what are your formulas? Your formula is PD is equal to A into FCD. So if I want PD value higher, I have to increase the area also and I should get the FCD value also higher. Now FCD value, getting FCD value higher is actually depends upon what is your slenderness ratio. If your slenderness ratios are lesser, FCD value will be higher. And so now the slenderness ratio depends on what is your length of the member. If the length is higher, obviously your slenderness ratio will be higher, L by R, right? If the length is lower, for the same given section, your slenderness ratio will be lower and ultimately your FCD value will be higher. Okay, so in this fashion you have to think little bit that when you select the section, if the length of the section is higher. Now yesterday or day before yesterday during our class we have learned about design of double angle section. Its length was 2.5 meter only. It's just half. Now we are using almost double value, 5 meters. So my slenderness ratio will be again it will be more, and if my slenderness ratio is more, my FCD value is going to reduce. I know that. So I'm selecting a section having higher area. See, the area requirement is 50 centimeter square, but I'm choosing a section almost having area 60 centimeter square. Okay, so in this fashion you need to think while do the designing. Otherwise you can select the 54.94, that section also, check whether it is safe or not. If not, then revise the section. That calculation will increase. Okay, so this logic you just put before designing the column section or compression member. That's why initially while discussing about the design of tension members, I inform you that when you design the compression member, always select the sections having more and more area, hmm, higher areas. So now I'm selecting ISHB 225 59.66. Now Omkar, whatever section you told, it was ISLB 225, right? What was that section? No, ISLB 325. Its area is also same. See here, 54.9. ISLB 325, 54.9. And here, the next section is ISHB 225, 50.94. Sorry, 54.94. Almost same area. It is having the same area, but the depths are different. Okay, depth is higher in case of ISLB. Here, depth of section is lower, but the other dimensions must be more in ISLB 325. That is, the thickness of the flange and thickness of the web might be more than this, and that's why we are getting the higher area. Okay, and the depth is also more. So you can try all these three sections. Today we will solve ISHB 225, but as a homework, as it will give you the practice also for designing, you can choose this section also. You can choose ISLB 325 also, and you can verify the values. See, not only the area, but also what is the class of the section, that is also important. The selected section, it should not be slender. That is also the another important criteria. So you just try out what are the section classification of these two earlier two sections, ISHB 225 and ISLB 325. If you are getting a class of the section better than slender, you can use that section also. Okay, so let us use now here ISHB 225 59 point sorry, what is the weight? 46.8. So I will just write down this. Select ISHB 225 at 46.8 kg per meter. It is the weight, huh? Always write down the full like this, huh? ISHB 225 at 46.8 kg per meter. This will represent, or it will give you the specific section. As I have explained you in steel table, you have two sections having the same depth. So if you mention only ISHB 225, it will become difficult to understand exactly which section you have selected. Okay. So what is the area, gross area? Just tell me gross area of this section.
59.66 centimeters square.
59.66 centimeters square. Then I will require some other properties also, because we want to find out its class. So for finding the section classification, I will require what is the width of the flange, what is the thickness of the flange, and what is the thickness of the web. Look into the steel table and tell me all these values. Along with this, we will also require the H1 value, that is the depth of the web only, and the radius of gyration values also. So just tell me all both the Rxx and Ryy values.
Ma'am,
Or
width of the
rather,
flange.
instead of xx, just a moment. Instead of xx, you should write down zz. Rzz. This is actually nothing but Rxx as per steel table and Ryy. Yes, tell me BF value.
Width of flange is 225 mm.
Okay,
Thickness of flange is 9.1 mm, and
okay.
thickness of web is 8.6 mm.
H1. You might get H1 value on the next page.
180.5.
180.5. Then RZZ and RYY.
And RXX is 9.58 centimeters,
Hmm.
and RYY is 4.84 centimeter. 84.
4.85.
84.
Okay, 48.4 mm. I'll write down in mm only. Okay. Now, what is the support condition given in the problem? Or before going to the further calculation, let us find out what is the class of the section. So, let us find out classification of of using this section. So, section classification, we will go to the IS code again and page number 18. Here, we have to find out the class of the section for flange and web separately. So B by TF, that is the first ratio for flange. We'll just write down for flange, outstanding element. B by TF is the ratio. B is normally taken as BF by 2 by TF. So BF value was, I think, 225 by 2 divided by TF is 9.1. So what is this value?
12.36.
12.36. And what is the limiting value here in the table? For rolled section, it is 15.7 epsilon. So this value is coming less than 15.7 epsilon. So flange is semi-compact. Okay. Then for web, the ratio is, for web of an I section, axial compression, d by tw is the ratio, and the limiting value is 42 epsilon. So this is d by tw. D we normally take as h1, so h1 by tw. I hope everybody remembers all these steps. H1 value is 180.5 and TW was 8.6. So what is this value?
20.99.
20.99. And I will go back to the code here again. For axial compression, the value is here 42 epsilon. Okay, so this value is less than 42 epsilon. So web is also semi-compact. So what is the overall class of the section?
Semi-compact.
Yes. So section is semi-compact. Okay. Now, so the same section we can use further as a column. Now similarly, as we have calculated the class of the section, one more class we need to find out, that is the buckling class. So let us find out that first and then we'll go to the slenderness ratio. So for finding the buckling class, we have to refer table number 9. Now in this table, see here for rolled I section, we have to refer the first row. The dimensions of I sections are shown here, and according to this dimension, so based on this diagram, we need to calculate all these limits. So we have to find out first h by bf, and we have to compare that with 1.2. Okay, so h is nothing but the overall depth of the section here, and bf is the width of the flange. So let us find out the buckling class. Buckling class for as per the ratio, h is 225 total overall depth of the section, and bf is also 225, so this value we are getting 1. Now comparing with the value given here, if it is greater than 1.2, then we have to use this clause. Now the value is coming less than 1.2, right? The value is coming less than 1.2, and see here, TF value. What is the TF value given?
9.1 mm.
9.1. So TF is in between. It is less than 40. See, actually what is happened here, when the H by BF value, if it is greater than 1.2, then we have to use these values. It is less than 1.2, go to the next row here. So the H by BF value is less than 1.2, we have to refer this. TF value is less than 100, so we have to, or our class, buckling class will be like this. Okay, so H by BF value is less than 1.2 and TF is less than 100. So we'll write down here, this is less than 1.2 and TF value is 9.1 mm, which is less than 100 mm. Okay, so for this condition, the buckling class is given here is as buckling about ZZ axis, the buckling class is B. Buckling about YY axis, the buckling class is C. So write down this here. Therefore, buckling about ZZ axis class is B, and buckling about YY axis class is C. See here now, we are getting two different buckling classes for considering two different axes of buckling. Okay, now let us see. I will try to draw a column section. Suppose this is our I section. Okay, this vertical axis is nothing but our YY axis, and this horizontal axis is ZZ axis. Okay, now YY axis is normally considered as the weaker axis, and ZZ axis is considered as the stronger or major axis. So if I will try to draw a 3D diagram of the column here, suppose this is my I section like this. Okay, and Z and Y axis we have already shown over here. So what is given in the problem? What is given in the problem statement? We'll just read the problem statement again here. It is of 5-meter height, hinged at both the ends, and braced at mid height for restraint against buckling about weaker axis. Now my YY axis is the weaker axis. Okay, and to avoid the buckling about YY axis, there is a bracing provided at the mid height. So if I want to see the uh, diagram here again, the YY axis, as it is a weaker axis, the buckling about YY axis, it will be like this. It will buckle like this. My column will buckle like this. Okay, about Y axis. And when we consider buckling about Z axis, the column will buckle like this. Okay, now to avoid this buckling, which is about the weaker axis, there is a bracing provided at mid height of the column. It means there is some support provided at the mid height over here. So my column is actually having a height below this also. Okay, along Y axis. And along Z axis, it is having a full length because there is no any bracing provided here. See, this is the normal type of a situation which we normally observe in any industrial building. I will just try to show you the diagram for the industrial building, how these bracing systems are provided. Suppose we have a industry. This is a certain length of the industry, and we have provided the I sections like this. Okay, at all these locations, these are the columns, and these are like this. Okay, at a specific distance we have provided the columns in the industrial building. And to avoid the buckling about the weaker axis is normally the Y axis, the bracing systems are provided like this. To the column is further having a height below this also. So the column is actually having a certain height like this. Okay, so the bracing system is provided like this. So actually, when a buckling of a column takes place, as it has a support at a mid height over here, the column will buckle. Only this part of the column will buckle like this. Okay, here also, if the column will buckle, it will buckle between these two heights only. But when you consider this direction, the column is free to buckle to its full length because there is no support provided here. We do not provide the bracing like this. Otherwise, your entrance to the industrial building will get closed. Okay, so this is the side view of the building, and here is your truss like this. The truss is resting on your column like this. This is the second truss. So here is my second truss, then there is a third truss like this. Is it clear, guys, now? So how the bracing system is provided, and when the buckling of the column takes place along y-axis where there is a support, the length of the column gets reduced. Whereas when in opposite direction, when you consider, this is the z-axis and this is the y-axis. Okay, so in opposite, in z direction, or when we consider buckling about z direction, there is a full length available. but it is our stronger axis, so normally buckling takes place about the weaker axis, and to avoid that buckling about weaker axis, we provide the bracing system like this. Is it clear, guys?
Ma'am, these
What is done in this particular case?
ma'am, and
Yes.
these bracings are connected to the web or the flange of the eye section.
Flange. See how I have drawn the cross section here. This is the flange, no?
Okay.
This is my eye section. So this is flange. This is flange. This is web. And I want to provide the. Are you getting this or not?
Yes, ma'am.
So, as per the given criteria, now I will just write down the support conditions and the effective lengths. So, what is the criteria? Both ends hinged, right? Both ends hinged. And when we consider the buckling about ZZ axis, I am having a full length. I'm having a full length of the column. Now, instead of considering full length for the hinged condition, what is the effective length? That we have to see also. So, looking into the table 11 now, which gives us the effective length values. See, this is the table which can be used only for the columns. We are not supposed to use this table for strut members, that is for single angle or double angle sections. By using these when we design the members of the truss, we never use this table. This table is applicable only for the columns. Okay. So here, what is the condition? Both ends are hinged. So this is our condition. This is our condition. Both ends of the column are hinged. So in that case, the effective length is taken as 1L. So my effective length is equal to 1L. And the original length is equal to 5 meters. The original length is 5 meters. So this is multiplied by 5. So I am getting effective length in z axis as 5 meter. Okay. But when I consider the buckling about y axis, the total height of the column itself is reduced because of the provision of bracing. So when I consider the buckling about y axis, my effective length is to half. So I will write down 1 into 2.5. So what is the value? It will be 2.5 meter as the effective length when I consider buckling about y-axis. Okay. Now when I want to find out the slenderness ratio about ZZ axis, that is when considering buckling about ZZ axis, I have to consider RZZ value to find out the slenderness ratio. And when I consider buckling about YY axis, I have to consider RYY to find out the slenderness ratio. Okay. So I will just write down here lambda Z or lambda ZZ is equal to L. Similarly, lambda YY will be equal to L effective YY upon RYY. Okay. So L effective RZZ value was 95.8. Am I right?
Yes, ma'am.
So what is this ratio, Kitty? Do the calculation little faster, guys. I have to complete the concept of built up column also.
52.19.
52.19. And here the lambda y by L effective is 2500 divided by R y by was 48.4. So what is this value?
51.65.
51.65. Now, out of these two, the higher slenderness ratio will be selected if the buckling class would have been same. Now, here the buckling class is different. About ZZ axis, the class is different. Above Y axis, the class is different. So, we have to make use of both the slenderness ratio separately, and we need to calculate FCD to FCD value. One about ZZ and one about YY.
Ma'am,
Okay. So, I will again write down here.
ma'am,
Yes.
ma'am, can you explain about that? The length, effective length about y axis we have taken 2.5. I didn't get it.
Hmm. Because we have provided bracing at mid height. So when bracing is provided, the column height is reduced to mid value or the half the value. I've explained everything here now. I've explained this through diagram, how the bracing is provided here. हे समजलं नाही का तुला?
मग ते
हे
कळालं
एक्सप्लेन केलं
होतं,
होतं ते?
पण फक्त लेंथ अर्धी का घेतली ते नाही.
हां, मग
अच्छा.
मग आता मी सांगितलं ना, इथं ब्रेसिंग लावल्यामुळं मिड हाईटला बकलिंग केवढं होईल कॉलमचं? एवढंच होईल. सो एवढाच कॉलम इफेक्टिव्ह लेंथमध्ये येणार. सो वी हॅव कन्सिडर हाफ द लेंथ.
ओके.
या बाजूला नाहीये प्रोव्हाइड केलेलं ब्रेसिंग सिस्टीम, सो इट विल बकल फॉर द फुल लेंथ.
येस मॅम. गॉट.
So when we consider buckling about ZZ axis, the buckling class is class B, so we have to refer table 9B to find out, and lambda ZZ value. So what is the lambda ZZ value? It is 52.19. And have to find out FCD. Okay, so let us go to the IS 800 table 9B. Table 9B, this table, which is given on page number 41. Refer this table. Our ratio is, refer this table, table 9B. Our ratio means the slenderness ratio is 52 something, 52. So it will lie between 50 and 60, and the corresponding to that, in the 250 value, FY value column, find out these values. So FCD value is in between 194 and 184, 181. Okay. So for 50 and 60, interpolate the value. We have the lambda values 50 and 60. We want to find out for 50.52.19. FCD values are, for 50 it is 194, 194 and 181. So 194 and 181. What is this value? Do the interpolation quickly and tell me the value. .
191.153.
191 point.
153.
Yes, again
153.
15. Okay. 191 point. Okay. 15. I have taken 15. Okay. So this value we have obtained about Z buckling. So I will simply write down FCD Z is equal to square. Now when we consider buckling about y axis, buckling about y, we have to consider lambda y. What was the lambda y value? It was 51 point, right? 51.65.
65.
And for Fy equal to 250, now we have to refer table. What is the buckling class about y axis? It is C. So we have to refer table 9C. Okay. So again from table 9C, tell me now the FCD value for lambda equal to 50 and 60, because this value is again lying between 50 and 60. You have to refer table 9C because our class of buckling is C. So I will go to the next page, table 9C. For 50, 183 and 168. 183 and 168. So interpolate the value in between these two and tell me FCDY.
180.53.
180.53 Newton per mm square. So we value is to be selected for calculation of PD. So just write down using least value of FCD, we can calculate PD as PD is equal to area. It was I think 5,000, right? 5,000 mm square into FCD. We were having two values. First was 191.15 and second was 1, just written here, 180.53. So out of the two, this is the least value. So we have to use this value, 180.53. So put that value here, 180.53. What is the value? PD. Come on fast.
900.
90.65.
164.
Can you tell me again?
902.65 kilonewton.
902.65 kilonewton. And this value is, wait. 5,000 was the required area, na? We have to use the um, area of the section. What was the area of the section? Area of the selected section should be used here.
Five nine six six.
It was 5966. That value should be used here. So now tell me what is this value we are getting.
1077.04.
Hmm. So this value is safe. Okay, this is how we design the columns. Obviously, the case support conditions given in this problem was simple, both ends hinged. You may get the support condition like one end hinged and another fixed, which is the normal criteria for any kind of the industrial shade. But for calculation purpose, our calculation becomes easy when we consider both ends hinged. Whenever we consider the fixed support, our calculation becomes very difficult. So in case of industrial shade also, when we do the analysis for footings, see, after designing of column you need to design the footing. So for footing also, when we consider the a condition between column and footing, though it is fixed, we consider it as a hinged connection and we do the analysis, because that becomes easy. If the connection between column and footing is considered as fixed, our analysis will become complicated. Okay, so it is assumed as hinged and then the further analysis is done. So both ends hinged, that criteria can also be chosen, normally chosen for the industrial shades columns. So in your term work also, when you design the column, you consider the same criteria, both ends hinged, okay, for the column, and then you design the column. Is it clear, guys? Any doubts here? Now you just imagine that what are the height of the industrial shades given for different groups. It is not 5 meter, it is 10 meter, 12 meter, 15 meter heights are given. You can just imagine the columns having 15-meter height. It will definitely buckle. So in every problem for your groups, within your groups, you need to provide the bracing system as I have shown over here through this diagram. Okay, the bracing will be provided to the columns like this. You consider the height of the column reduced to half. Now half, when the height of the column is say 10 meter, when we reduce the height to half, see the total length of the column we are getting as 5 meters. Okay, you can just imagine what is the value of the slenderness ratio. When we have considered the full height of the column, the slenderness ratio is around 52. Okay, 52. If you consider the total full length 10 meter, it will reduce much more lesser to that. And if you look into these tables of IS 800, if your value is say between 30 to 40, you can just check what are the FCD values here. It is just 211, 198. These values are higher. Okay, sorry, I should say in opposite fashion. The KL by R value will increase when you go to the higher length of the column. And see here the value of the FCD values are getting reduced here. Okay, so in any case your slenderness ratio should be less than 180. That is again the important criteria which I forgot to write here. So just make the correction in your notebook here, that the slenderness ratio whatever we have calculated, it should be less than 180. This should be less than 180. This should also be less than 180. Okay, so if the length or height of your column for your term work, if it is say 15 meter, you need to provide two bracing system like this here. Hmm. I have shown here in this diagram two bracing. So my first height will be 5 meter, then second will be 5, and third will be 5. And for that 5-meter height only, about y axis I am going to consider the calculations. And about z axis I will consider full height. Okay, so columns are also normally oriented like this. Hmm? We place the columns like this only, and we do not place the column like this. We do not place it like this. Okay, this is the wrong position. This is the correct position. Okay, along the length of the industrial shade. If see, this is your top view. If this is the top view of your shed, okay, The columns are placed like this. The columns are placed like this. Always. So that above the weaker axis we can provide the bracing system here, either in the interior side or the outer side of the building. We never place the column like this. We never place the column like this. Okay, this is the wrong practice. This is the correct practice. Okay, is it clear to everybody?
Ma'am, is there also a design of connections for this column?
No, no. Actually, that is the different part. Actually, column to footing connection and column to truss member connection, that requires some different criteria that we have not included here. So don't consider those connection designs in your term work. ओके,
Okay.
प्रॅक्टिकली असतं कनेक्शन, तर असतंच कॉलम आणि फुटिंग मध्ये कनेक्शन असतंच, ते डिझाईन करावंच लागतं प्रॅक्टिकली. येस, पण आता टर्मवर्क मध्ये नका कन्सिडर करू, कारण ते परत खूप मोठं होईल ते सगळं, आणि ट्रूली स्पीकिंग दॅट मच टाइम इज नॉट देअर रिमेनिंग नाऊ, आणि ते इन्क्लुडेड पण नाहीये तुमच्या सिलेबसमध्ये.
मॅम, पण त्याच पद्धतीने करतात ना, जसं आपण सिंगल अँगल आणि डबल अँगल केलं तसं?
नाही नाही नाही, नॉर्मली मुवमेंट येतात कॉलमला, कॉलम टू फुटिंग जाताना, मग मुवमेंटसाठी सुद्धा तुम्हाला कनेक्शन डिझाईन करावं लागतं, आणि मुवमेंटचं कनेक्शन डिझाईन वेगळं असतं. यू हॅव डिझाईन नाव द कनेक्शन फॉर ॲक्सियल फोर्सेस, सॉरी, फॉर द शिअर फोर्सेस ओनली. हां, ॲक्सियल फोर्स म्हणजे टेन्साईल फोर्स असेल, मी तुम्हाला टाईप्स ऑफ बोल्ट्स किंवा फोर्सेस प्रमाणे जे काय टाईप्स होतात ते मी सांगितलं होतं, की बोल्ट सब्जेक्टेड टू शेअरिंग ॲक्शन, bolt subjected to bearing action, bolt subjected to tension, and bolt subjected to movement. तर टेन्शन आणि मुवमेंटसाठी वेगळ्या पद्धतीनं थोडं डिझाईन करावे लागतात बोल्ट्स. तुम्ही आत्ता फक्त शेअरिंग आणि बेरिंगसाठी करता डिझाईन. ओके, दॅट इज सफिशियंट फॉर ट्रसेस. ट्रससाठी ते सफिशियंट आहे, म्हणजे दॅट कनेक्शन डिझाईन इज मोस्टली ॲप्लिकेबल फॉर दी मेंबर सब्जेक्टेड टू ॲक्सियल फोर्सेस.
Yes, ma'am. Got it.
Okay, now we almost have crossed 10 o'clock. I actually wanted to explain you the concept of built up column, but do you have any further lecture at 10:15? Guys? Omkar?
Ma'am, students are having survey lecture, but concrete lecture is cancelled. So means half class is having lecture.
Mm. So can I extend my lecture for say 5 to 10 minutes? I just wanted to explain you the concept of built up column.
Yes, ma'am.
Okay, just 5 to 10 minutes. Huh? I will simply, or I will directly go to the code now. I hope everybody is able to see the code copy. I have to rotate it again. So in this code, you can see these diagrams. These are the diagrams showing the built up columns. Okay, these are the diagrams showing built up columns. Now built up column means what? I will draw a simple diagram here to explain you the concept of built up column. When the columns are subjected to very heavy loading, say more than 1500 kilonewton, or when they are subjected to movement also, that is eccentric loading, then instead of using a single eye or single channel section, we use the double eye sections. So these double eye sections are placed side by side like this, and they are connected here at their flanges. They are connected here at their flanges. Okay, if two channel sections are used, then the channel sections may be placed like this, face to face. This is a top view I'm showing, and the channel sections may be and these are connected over here along the flanges, or they may be placed back to back flanges. Okay, so this is a top view. When you see the front view of the column, so if I will try to draw again a 3D diagram here, this is my first column, and this is the second column. Now when these two columns are placed side by side, there is a criteria what should be the spacing between the two columns, and it is calculated as per that criteria only, normally based on the moment of inertia required. And then these two columns are connected to each other by using certain connection process. I am right now showing here a lacing system. There are two ways to connect these columns to each other. To make them two sections together, these two sections will not behave like a part of a single column. When we connect them together, this will act as a single column only. When we are not connecting, these are the two different columns. Okay, why we need these two sections? Because obviously when we use two sections, the cross-sectional area of the entire column will be increased, moment of inertia will be increased. In other words, the PD value will increase, the load carrying capacity of the entire section will increase. Okay, now these two columns are connected to each other either by using a lacing system or a battening system. And this is the important connection: lacing system or battening system, which are battening system. Okay, so these systems are shown here in this diagram. This is the lacing system. You can see here they have given the example over here as two channel sections. See, two channel sections which are placed face to face, and these are connected at A and B. This is the A face and the B face. This is the top view of your column. And when we see the A face here, see here lacing on face A, it is provided like this. So these are this member is nothing but your flat. It is called as flat. There are again now different types of these sections. A plate section, normally the width of the plate sections are more than say 25 mm, and the flat sections in which the width of the sections is normally 10 mm, or in short it is less than 25 mm. Okay, so when the width of the sections are less than 25, it is called as flat. When it is greater than 25, it is called as plate. Okay, so these are called as flats, FLAT, flats. And these are connected like this to the two sections to be, make these two sections behave like a one column. On face A, it is connected like this. On face B, it is connected in the opposite fashion so that it will look like a mirror. Its mirror image will be produced. Its mirror image should not be produced on the another side. Okay, if on one side, if the first flat is like this, on the another side it should be in opposite direction. It should not be like a mirror image. Many times the force is so heavy that the single lacing system is not sufficient to connect the two columns. So instead of single, the double lacing system is provided like this. Okay, so two flats connected to each other in a crossed direction. This is called as the double lacing system. Okay, now when we consider the lacing system, whatever the force acting on the column is vertically downward. It is an axial compression. Because of that, the horizontal force is developed at this connection between the joint of the two lacings. The horizontal force is considered, and because of that horizontal force, the axial force is developed in these lacing flats. So when the columns, built up columns, are connected together by using lacing flats, the lacing flats are subjected to axial forces, and these are designed for or designed like a tension member as well as compression member. So because the force is acting in this fashion also, and it may act in this fashion also. Okay, so the, in other words, if we can, no, I can't write over here. So if a force is acting vertically downward here, there will be a horizontal force acting at this joint, and because of that the axial tension and compression will be developed in the lacing flat. So lacing flats are designed always like a tension member and compression member, like the members of the truss. Okay, this is the one or the first system of connection. Second system is called as battening system, in which the lacing flat, the horizontal plates are connected here. So these are the flats, whereas these horizontal members are nothing but the plates. Now this example is actually giving a combination of cross members and horizontal members. So it is a double laced along with the batten plates. And if I want to show you simply or only the battering connection, it is here. Okay, so in case of battening system, only the horizontal plates are provided like this. Okay, and when these horizontal plates are subjected to this vertical loading which is acting in the column, the plate is subjected to bending moment and shear force. So these plates are designed like a beam. These plates are designed like a beam. See, you can now just imagine how it is difficult to design, not difficult, but it is a tedious task to design the columns, built up columns. You have to design the column first, and then you need to design this connection system also. Now the connection, if it is done by the lacing system, design that lacing flats either like tension and both, normally tension and compression member. And when you are using the battening system, design these batten plates also like a beam. Okay, so that design steps goes on increasing and becomes complicated. So now how these forces are calculated, what is the exact difference between lacing system and battening system, everything is given here in clause 7.6. In clause 7.6, the laced columns, what are the criterias? Now there are different criterias. What should be the width of the lacing flat? What should be the spacing between the two lacing? This vertical distance, there is a limitation for this vertical distance. What should be the width? What should be this angle? All these are to be designed as per the specification. Similarly, when you design the batten system, again, what should be this spacing between the two batten plates? What should be the width of the batten plate? And what should be the length of the batten plate? How many batten plates are to be provided for the connection? Everything we have to design as per the specifications. Okay, and what should be the thickness of the plate? That also have a criteria. Thickness of the batten plate as well as thickness of the lacing flat. And everything is given here through this clause number 7.6, which is there for lacing system connection, and the next clause is 7.7 for batten columns. Okay, so the detailed design of this is not there included in your syllabus. For earlier batches it was there. Earlier batch students used to design the built up column, they designed the lacing system, batten system, and normally the theoretical question was asked in the examination, what is the difference between lacing and battening system. Okay, so practically we always design the built up columns whenever there are heavy loads are expected, whenever the movement is expected on the column, and whenever the vibrations are expected on the column. So whenever you visit the railway station, you do observe the various columns provided on railway station. All these are the built up sections. Okay, if you visit, see, based on this normally we schedule the site visit on Pune railway station. There you can see huge number of columns, built up columns, which are connected by battening system and lacing system. So if you really want to understand what are the steel structures, better you visit any railway station. Almost all railway stations are constructed by using the steel sections only. Okay, we never go for RC structures on railway stations. Okay guys, so this is about the concept of built up column. Detailed design is not included for your syllabus, so I just wanted to explain you the concept here. So we'll stop here today, and in the next lecture we will start with your third unit, that is design of beams. I'm giving you another link for the attendance in the chat box. All of you please give the attendance through the link only. Okay.